Good afternoon, and welcome to our second session of the day. And it's all about quantum. It's my pleasure to welcome our next speaker. Andrea Morello is the Professor of Quantum Engineering at the University of New South Wales in Sydney. He's an Australian Research Council Laureate Fellow and a member of the American Physical Society. He's received numerous awards, including the Landauer and Bennett Award for Quantum Computing. Now, his research interests further extend into quantum chaos, quantum foundations, and quantum sensing. He's a passionate science communicator and teacher. His YouTube videos have gathered over 10 million views. He also led the creation of the world's first bachelor's degree in quantum engineering at the University of New South Wales. Here to explore how the limitations of our vocabulary impact our understanding of quantum reality, please give a very, very warm welcome to Andrea Morello.
Thank you. Thank you all for coming to this talk, and thank you again to Ines and to Tony and to the whole Innotribe tribe for inviting me here and giving me this really quite challenging but stimulating task of discussing the topic of lost in translation, where the translation is between the natural language that we all speak and the physical world and the language used to describe the physical world of quantum mechanics. Quantum mechanics is a theory of the world that underpins some of the most exciting and revolutionary technologies that are being developed in the world right now, some of which may and probably will have an impact in the financial sector in the next decades. So what I want to do today is a program that starts with covering language, so how language is related to experience and how we describe the world. Then I want to talk about understanding. What does it mean to understand something and the experience that goes with that? And then I'm going to quantum mechanics, which is unfortunately often described as a weird and counterintuitive theory, and I want to debunk that. And I'm going to take upon myself the challenge of explaining to you quantum entanglement, which is allegedly one of the most counterintuitive phenomena in quantum mechanics. I'm going to introduce the correct language to describe quantum entanglement and explain it to you. My objective today is for you to walk out of this and think, is that it? Is it really that simple? It is. So let's start with language. You can take a dictionary and see what is the definition of language. This is the Oxford Dictionary. And so there's actually two of them. One is kind of technical. It says the principal method of human communication consisting of words used in a structured and conventional way and conveyed by speech, writing, or gesture. And the second one is a bit more interesting. It's a system of communication used by a particular country or community. So the second definition acknowledges the fact that language is contextual, it's cultural. And there's many ways to illustrate that. Most people think that the Eskimo language is the one that has the most words for snow. It turns out, I only learned it last week, the Scot one has the record. There are 421 words for snow in Old Scottish language. Go figure. In Hawaiian indigenous language, there is only one word for snow and ice. That actually doesn't distinguish the two. If you want to say snow, you need to say haukea, which means the white how, where how is the common word for snow and ice. Obviously, because in the old days, Hawaiian people did not see the snow ever, right? So it's a very simple way to illustrate how exposure and experience influences the way we use and create language. Now, it actually goes beyond just the existence of words. This is actually a personal story. I used to have a Russian girlfriend who was fabulous. We had a really great time together. And I often found myself, we're having a good time and say, I'm Italian. I say, la bella vita, what a beautiful life. And then once I asked her, how do you say la bella vita in Russian, And she growled at me and said, we do not have concept of beautiful life in Russia. Now, of course, they have the words, so you can say beautiful life, it is krasivaya жизнь. But if you talk to a Russian person and say, "Красивая жизнь," they will frown at you and say, "What are you talking about? This makes no sense." Because it's just not part of their cultural fabric, right? So even when the words exist, there is more context around it that matters. Which brings me to understanding. Now, what is understanding? You can go, and I encourage you to do it. It's kind of fun. Go to your favorite dictionary and look up the definition of understanding. It's remarkably dissatisfying and often very circular. Like, understanding means understanding. Like, it's actually really bad. So I pulled up one from Wikipedia, which is the least worst of the ones I could find. And so it starts very technical, because understanding is a cognitive process related to an abstract or physical object, such as a person, situation, or message, whereby one is able to use concepts to model that object. All right. The last sentence is more on point. Understanding is a relation between the knower and an object of understanding. So it's a little bit circular, but it acknowledges that understanding means creating a relation between you, the person, and something that you wish to absorb as part of your understanding. So as an academic, both a professor and a researcher, I deal with understanding my whole life, both for me to understand, the research that I do in quantum mechanics and quantum computing, and then to teach it to the students at various levels to help them understand these disciplines, which are sometimes quite complicated. So I actually have a first-hand experience, both on myself and on hundreds of people that I've trained over the years, on what it means to understand. So I'm going to give you my own definition of what understanding means. And it's something like, understanding is the ability to describe a concept or idea or a thing or an experience within the context of your own lived experience, something that you are personally, intimately connected with, something that you have experienced before and forms part of what is your own body of knowledge. That is what understanding means. It's getting some new piece of information and say, it fits in this box that I know and that I've labeled for myself. That's what it means, understanding something. And so I want to mention here one of my favorite film director, Krzysztof Kieślowski. His most famous films were the Trois Couleurs, the three colors. He also did this beautiful series of 10 one-hour movies called the Decalogue. It's a beautiful, gripping thing. And then he gave an interview at the end of the Decalogue where he kind of explained how he went about developing that. And he said something that really struck me, along the line of, you cannot talk about something that has not been described. That really spoke to me. What did he mean by that? So as a filmmaker, he saw one of his roles as providing people with a common scene experience so that they can talk to each other, they can understand each other on the ground of having seen a movie, having seen a documentary. Describing things is the starting point for being able to interface with someone else and find a shared understanding. This will come back when I talk about quantum mechanics, so remember Krzysztof Kieślowski for now. Now, let's get into quantum mechanics, which is actually my subject matter expertise. So what is quantum mechanics? I'm going to give you an old school answer. Quantum mechanics is the description of the behavior of physical objects at the microscopic scale. So quantum mechanics completely regulates the behavior of atoms, electrons, photons, things at a very, very small scale. I call it an old answer because it's actually it's still correct, but it's incomplete. Now, once you look at what quantum mechanics does and what actually happens at that microscopic scale, you encounter phenomena like quantum superposition, quantum entanglement, and as soon as I start using these words, which are plain English language words, you start to cringe, right? Superposition, things can be in two places at the same time, they are entangled by this spooky thing, and that's when things go haywire, right? So much so that there is famous great genius of physics, Richard Feynman, and he still gets quoted saying, if you think you understand quantum mechanics, you don't understand quantum mechanics. Now, I wish I had that dress that Jasna Rock used yesterday in the opening of Innotribe. I would go bright red with rage. This quote really, really upsets me because it really did not age very well. It's true that it's not simple to understand quantum mechanics, but much of the problem around it is that we use the wrong language. So what I want to do today at the end of this presentation is to show to you quantum mechanics in the right language. Okay? And then we go to quantum entanglement here, just to throw dust on some of the other geniuses. Albert Einstein, he had this big problem with quantum entanglement. It's like a spooky action at a distance. So if I have to explain to you what quantum entanglement is in plain English, is the property of quantum systems of losing their individual nature and existing only in relation to each other. And this correlation persists no matter how far apart those physical objects are. So when you say it like that, it sounds, oh, man, what is that? It's counterintuitive and weird. In reality, it's everywhere. You contain a billion of a billion of a billion of entangled particles. Every chemical bond contains a pair of entangled electrons. The reason you and I exist in this room and not just in some plasma in empty interstellar space is because of the chemical bond, which is a consequence of quantum entanglement. So it's real, because we all are. But we don't have the senses, we don't have the receptors to experience quantum entanglement firsthand. Now, interestingly, there may be living creatures that have that. This really cute little bird is called a European robin, and it's a migratory bird that in some seasons of the years flies from North Africa to Northern Europe all the way to Scandinavia. And people have been wondering, how does this bird know where to fly? And so by now it's clear that it uses the magnetic field of the Earth. It literally has a magnetic compass. It senses the direction of the Earth's magnetic field, and so it flies straight north. And then people try to figure out what that magnetic compass actually is in the bird. And this is still, a subject of study. It's not completely settled, but there is some initial evidence that what the bird does is that it has in the eye, in the retina in the eye, it has a receptor that contains pairs of entangled electrons, which in itself is not uncommon. As I said, you are a billion of a billion of a billion entangled electrons. But those electrons are only very loosely bound, so that if a photon of green light hits, which is part of the wide spectrum, if a photon of green light hits the retina of the bird, those two electrons get ripped apart. And then when they're ripped apart, they have a spin. The spin is like an atomic scale magnetic dipole. The spins start to precess in the Earth magnetic field. Eventually, they can recombine, but only if they remain entangled. When they recombine, the energy of recombination is released into the optical nerve of the bird, and so the bird receives the stimulus from the recombination of the entangled electron. And it seems that the entangled electrons remain entangled only if the bird is aligned along the direction of the Earth magnetic field. Whereas if it's going sideways, the precession disentangles the electrons, they don't recombine anymore, and it doesn't get the stimulus in the optical nerve. So again, to put it in plain English, what it means is that this bird can see quantum entanglement. And then it's kind of fascinating to think, what if we could have that receptor implanted in our retina? Could we see quantum entanglement? How would our perception of the world change if we had a receptor like that bird has? It's pretty fascinating to think about, all right? Now, let me move to the second definition of quantum mechanics, which is the modern one. I would say that quantum mechanics is just, in general, the description of physical objects whose behavior is affected by the Heisenberg uncertainty principle. The Heisenberg uncertainty principle is the foundational law of quantum mechanics that says that an object cannot be in a precise position and with a precise velocity. The product of the uncertainty on the position and on the momentum, which is mass times velocity, must be larger than a fundamental constant of nature that's called the Planck constant. Basically, what it says is that nothing can ever stand completely still. It needs to have some degree of uncertainty in velocity and some degree of uncertainty in position. Any physical object whose behavior is substantially affected by this is a quantum object. What I'm showing here for you is an electronic device. It's a small electronic circuit. You see the size scale. There is 3 micrometers, so the whole thing is about 10 micrometers. 10 micrometers is the thickness of a human hair. Like mine is a bit thicker than that, but if you have thin hair, your hair is 10 micrometers. So it's small, but it's not crazy small. Like I'm short-sighted. If I take off my glasses, I can see that thing on the naked eye, right? So that thing is an electrical circuit, and there's an indicated there, it's called tunnel junctions. It's not a closed circuit. It's an electrical circuit with some breaks. So normally, if you're a classical electronics engineer, you would say, well, no current can circulate in that circuit because it's not actually closed. But in quantum mechanics, when an electron gets to this point, it's not exactly here. It's here with some quantum uncertainty, so it can leak to the other side of the insulating barrier. So you can actually have current flowing through, even though classically shouldn't. And then, for reasons I won't go into, in this circuit, set up like this, you can have a superposition of a current flowing clockwise and a current flowing counterclockwise. This is a macroscopic current. It's like microamps of current. It's not a tiny thing. So this is to illustrate that this is not an atomic scale object at all. It's a macroscopic thing, and yet all its behavior is determined by the laws of quantum mechanics. That's why we need this new definition of what it is. And so this brings me to what is called the second quantum revolution. So the first quantum revolution was just learning quantum mechanics, realizing that the classical laws of physics are not complete. But the second quantum revolution is to create, engineer, build devices that do not exist in nature and that have new functionalities that are completely unprecedented. So the glaring example is a quantum computer, and there outside you see a reproduction of a quantum computer made of superconducting quantum bits, which are a modified version of the circuit I showed you before. Quantum sensors, quantum communication devices, and I also want to mention quantum probes. So quantum probes are tools that use quantum mechanics to make quantum mechanics visible to us. I want to give you an example here. This thing is called a scanning tunneling microscope. This was invented in the 1980s in Zurich. And it's an electronic circuit that uses the phenomenon of quantum tunneling. So there is a tip, you see there, that is hovering over a surface of some material. And then there's a circuit there, there's a voltage applied to that. So that would be, again, an electrical circuit which is broken. The tip does not touch the surface. So if you're a classical electronic engineer, you will say, well, that's an open circuit. There should be no current flowing there. In reality, there is, for the same reason. Once the tip comes very, very close to the surface, an electron at the end of the tip is not exactly there. It's there with some quantum uncertainty, so it can also be on the other side. And it tunnels into the body of the material, and from there it can be collected to the other side, and then you measure the current that flows through that circuit. As it turns out, the current depends exponentially on the distance between the tip and the surface. So much so that if you scan this tip along the surface, you have to do it very carefully, so there'll be zero vibrations and so on. If you scan this tip and you plot the current as a color scale, which is what's on the right, you see the bright spots is where you have the maximum current. That's because there is an atom there. So the presence of an atom enhances the current in that circuit by a very large amount. And when you plot it in color scale, you can see literally atom by atom where the atoms are placed on that surface. Now, this is a really interesting story because that surface is the surface of silicon. Silicon is the material that underpins the totality of the digital era, the whole of modern microelectronics. And the crystal structure of silicon was understood, since the 40s or 50s at least. We all know exactly what it is. And we already had, in the 1980s, CPUs, devices made out of silicon, classical computers. So that was all done and understood and used even commercially. But when it came to the surface of silicon, people didn't understand why it behaved the way it did. Until this instrument was created, and then they looked at the surface of silicon and they found, this is a 2014 high-resolution image, but the first time it was seen was in the 1980s, not as nicely as this. I said, that's why it does what it does. That structure doesn't look like anything like the crystal structure of the bulk silicon. The surface reconstructs. And people never knew what it did until they saw it with their eyes. So this quantum probe is actually a way to give us access as humans to what happens at the atomic scale, and then we can make sense, understand what is happening on that silicon surface. This is another example. This one is from my own lab. So this is a circuit that was made in my laboratory. This was, in fact, the first quantum beating silicon. This was done in 2012. So what you see here, the shiny parts are metallic structure on top of a wafer of silicon. The one up here is just the tip. So you see the scale up there. That's 100 nanometers. So this is actually pretty small. That is the tip of a microwave antenna that's terminated by a short circuit. So if you pass an alternating current in there, it produces an oscillating magnetic field that is used to control the spin of an atom of phosphorus that we implant inside of the silicon chip. That's the thing here in blue. That's PowerPoint. You can't actually see it on this image, but I guess you can paste it on a PowerPoint slide. So the blue sphere and the blue arrow represent the atom of phosphorus, which has also a spin. Remember, the spin is the magnetic dipole, like a mini atomic scale compass that pertains to the electron. And there's also a spin on the nucleus of the phosphorus atom. And then this other thing here, this is basically a silicon transistor. It's a modified silicon transistor that is modified to have a peculiar way in which the current flows. It's called a single electron transistor because electrons flow one after the other individually. Don't have time to explain all this. But the way it works is this. So we have actually a 2-qubit system. The nucleus and the electron, we can pull an electron from the transistor in the spin down state, and then we irradiate it with microwave, and we rotate it to the spin up. When it spin up, it can escape the atom, and when it escapes, it unlocks the current through the transistor. And then after a while, there will be another electron from the transistor and gets sucked onto the atom, blocks the current. And then I can do two things. In this video, I'm showing you the case where I'm trying a different frequency, which would be the frequency at which the electron would respond if the nuclear spin was up. The nuclear spin is not up, so the electron does not respond, and so the current doesn't flow. Or I could do another thing, which is to flip the nuclear spin, and then see that when I try the original frequency, the electron does not respond, and the current doesn't flow. Now, this is a lot of blah, blah, and nice animations. Now I'm going to show you the real thing. So what you see here is just a video I took with my phone. That's the screen of an oscilloscope. So the pink line is the current through the transistor. Okay? So you see now it's basically 0 plus some noise, so there's no current flowing. And then at some point you will see, now I get all these spikes of current. What's happening there? What's happening is that I'm flipping that electron successfully, and then it escapes, and then gets replaced, and escapes, and replaced. And then you see it stopped again. And now you'll see it restart. Okay. What's happening there is that I am flipping the nucleus in the other quantum state. And now I flip it back. So I want you to ponder on this for a minute while you keep staring at this. You are watching, with your eyes, the quantum state of a single atomic nucleus. This is the sort of thing that, I studied quantum mechanics at university in 1996. My quantum mechanics lecturer told me you can never watch a single quantum object. You only have to look at ensembles. And now this is my daily life and my students' daily life. This is really the meaning of the second quantum revolution. We have created tools, probes, that interface us with the most profound and microscopic aspects of the quantum world, down to the level of a single atomic nucleus. You can watch it on an oscilloscope screen. This is the novelty. This is what Einstein didn't have. This is what Feynman didn't have. We have it. Okay? Now, can we use this? Well, in fact, this is helping and affecting the way we understand, the way we create an intuition for quantum. In reality, we had the language for quantum already for a long time. So in the next 20 minutes, 15 minutes, I'm going to take it upon myself to explain to you quantum entanglement. Okay? It will involve a bit of mathematics. We're going to take it slow, step by step. It's basically arithmetics. Okay? So bear with me. If at any point you feel like I'm offending your intelligence, good. It really is that simple. Okay? Now, the first thing we need to do is to have a shared frame of reference. Remember Kieslowski? You can't talk about something that hasn't been described. So, if you want to describe, for example, the position of an object in space, this is something you do every day without thinking about it, you need to have some coordinates, some frame of reference. So if I want to say, where is Ines? Somewhere. Oh, there, yeah. So if have you seen Ines? Oh, where is he? Oh, okay. So if I make myself a frame of reference where the origin of the frame is here in the middle of the stage, and this is the x-axis, this is the y-axis, and this is the z-axis, and someone asks me, where is Ines? Oh, Ines is at coordinate 5, 5, 1. So 5 meters in that direction, 5 meters in that direction, 1 meter high. If we have this common frame of reference, you can find exactly where Ines is. It's right there. Okay? So here I'll give you an example where there is some point in space, in three-dimensional space, which is the space we live in, that has coordinate 2 along the x direction, 3 along the y direction, and 4 along the z direction. And I can organize those 3 coordinates in a vector, which is basically an array of numbers stacked up in a column. So the vector 2, 3, 4 is the set of numbers that describe the positioning space of that point. We cool with that? Yeah? Right. Now we just turn up the formal volume a little bit. We can redo the same thing in the language of a vector space. It's not as fancy as it sounds. So instead of making a vector at the end of it, I'm going to make vectors at the start of the process. So I can say, all right, I'm going to define my reference frame by defining 3 vectors of length 1 that are all orthogonal to each other. And then every other vector is obtained as a combination of those 3. So I can make a vector of length 1 meter that goes in this direction, a vector of length 1 meter in this direction, and a vector of length 1 meter in this direction. And I call them U because it's unit length. So UX, what would be the coordinates for UX? Well, UX is 1 meter in the x direction, 0 in y, and 0 in z. So it's 1, 0, 0. UI is 0, 1, 0. UZ is 0, 0, 1. Okay? It's nothing magic here, right? And now that vector 2, 3, 4 that describes the point V is a superposition of the 3 basis vector multiplied by some coefficient, which is the coordinate. So I take twice UX, 3 UY, and 4 UZ, and I get some point up there where there is the lamp. Okay? It's nothing magic here, yeah? Now, the reason I'm telling you all this is because I want to get to the interesting stuff, which is quantum computers and quantum information. But before I go there, let's talk about just plain old digital information. So in classical computers, the ones you use every day for everything you do, information is expressed in a digital form, in the form of bits that can take values of zeros and one. Now, information is physical. Those zeros and ones are embodied by some physical object, which in the case of classical computer chips is the voltage at the terminal of a transistor. Okay? So when I say this bit is 0, what it means is that there is some electronic circuit at the terminals of which the voltage is about 0. When I say it's 1, there is a voltage that is not 0, and it's between 0.5 and 1.5 volts, depending on the details of the processor you use. That's what it actually means physically. But it represents digital information, zeros and ones. I can do the same with quantum objects. I can make a quantum bit that also is made of zeros and ones. And I gave you an example before from the circuit in my lab, where the quantum bit is, for example, the spin of a single nucleus. So I can call the 0 the spin up, and the 1 the spin down. But now, in quantum mechanics, the way I describe mathematically those bits, those quantum states, is with vectors. That's why I told you a whole story about vectors. So I have two possible values. And to have two distinguishable vectors, they need to be orthogonal. So if I now have 2 dimensions, right? 2 dimensions because there are 2 possible values. So if I only have 2 dimensions, like on a plane, I just need a vector of length 1 along x and a vector on length 1 along y. So there's a 1, 0, and 0, 1. Those are my basis vectors. I don't need the 3rd dimension now. Okay? 2 dimensions, 1, 0, 0, 1, just 2 vectors. But now, once I express them like vectors, I can also make a superposition of them. So if I have, let's say, here it's just on the plane, I have x and y like this, I can make a vector of length 1 if I take 1 over square root of 2 this plus 1 over square root of 2 that. It's a vector that goes at 45 degrees. So superposition is this crazy word. It's actually just the sum of 2 vectors. It points halfway through them. So in quantum mechanics, I would do exactly that. I make a superposition with the factor of 1 over root 2. For reasons I won't go into, the length of the vectors in quantum mechanics must be equal to 1. It actually has to do with probabilities. The probability of observation must sum up to 1. And so it's 1 over root 2, 1, 1. There's nothing magic or bizarre about it. That represents a spin that is pointing halfway between spin down and spin up. So it points this way. It's a spin that points horizontal. It's nothing magic, nothing weird, nothing crazy, nothing spooky. It's just, this is 1, so this is 0, this is 1, this is the superposition of 0 and 1. That's it. All right, let's get something a bit more useful. So 1 bit of information, be it quantum or classical, I mean, it's a nice curiosity, but you're not going to make any money out of that. So you need a lot of bits in a computer, right? So if I have 2 bits, classically, I can make 4 code words, 0, 0, 0, 1, 1, 0, 1, 1. Same for quantum, 0, 0, 0, 1, 1, 0, 1, 1. So physically, like in the physical world, it means that the 0, 0 code is obtained when I have 2 spins both pointing up. The 0, 1 is up, down. The 1, 0 is down, up. The 1, 1 is down, down. Nothing magic, nothing weird. I'm not. Now, how do I represent this with vectors? Now I have 4 combinations, so I need 4 orthogonal vectors. This is where your imagination needs to stretch a little bit. Like, we can talk about 2 dimensions, we can talk about 3 dimensions. You don't have the intuition for 4 dimensions, but I'm sure you can see that this is pretty simple. You just need vectors with 4 numbers, and they all need to have length 1 and be orthogonal to each other. So the first one will be 1, 0, 0, 0. The second one will be 0, 1, 0, 0. Then 0, 0, 1, 0, 0, 0, 0, 1. Huh? 4 vectors, length 1, orthogonal to each other in some 4-dimensional space that you can't imagine, but maybe you can. Okay? Now, as before, OK, no. So what I've done here is essentially guess or intuit what those vectors should be. Right? I just took the simple possible option. I can make this a little bit more formal and use a mathematical operation that's called a tensor product. It's really very simple. It just means if you have 2 vectors, let's call them A and B, which have their 2 coefficients, A1, A2, B1, B2, their tensor product is literally stacking them on top of each other, well, stacking the second vector twice on top of each other, and multiplied by the coefficient of the first vector. So A tensor B is the first coefficient of A times B1, B2, the whole vector B, and then the second coefficient, A2, times the whole vector B. So when you multiply it all up, you get A1, B1, A1, B2, A2, B1, A2, B2. Now let's give you a practical example. Let's say that A is the 0 vector, which is 1, 0, and B is the 1. So I do the tensor product, so I take the first element of A, that's 1, times the whole of B, and then the second element of A, 0, times the whole of B. I multiply, I get 0, 1, 0, 0. Guess what? This is exactly what I had guessed before. That's the 0, 1 is the 0, 1, 0, 0. But now I do it formally instead of kind of guessing it. Okay? So this is just to show you that this simple formal operation arrives at the same result that you will logically expect. Now, also in the higher dimensional space, I can make superpositions. So let's say I take a superposition of the 0, 0 vector and the 0, 1 vector. So I sum them up with the usual factor at the front, so the length is 1, and it becomes 1 over 2, 1, 1, 0, 0. Now I want to do the reverse. So I want to say, okay, I got these 4-dimensional vectors which represents the state of 2 quantum bits. What is the state of the individual quantum bits in that state? What I need to do is to reverse engineer the tensor product. So I need to find the 2 smaller vectors, A and B, such that their tensor product is that vector that I call V1. Okay? So I just recap here. This is what the tensor product does. So I want to find A and B such that they give me that result. So it's usually easier to start from the elements that are 0 because you know that something has to be 0 to give you a 0, right? So let's start from this one. So A2B1 is 0, and also A2B2 is 0. So because they're both 0, it's inescapable that A2 must be the one that's 0. You can't have both B1 and B2 being 0 because the length of B must be 1. So certainly, if these two are both 0, then A2 is the number that is 0. And then if A2 is 0, again, because the length of A must be 1, then the other element must be 1. So A1 is 1. So I've already reconstructed the vector A. A is 1, 0, which is the 0 state. And then once I know A, I know A1 is equal to 1, so that means that B1, B2 are 1, 1 times 1 over square root of 2. So I've already reconstructed the vector B. So that means that that vector there, in 4 dimensions, is the tensor product of the 0 vector with the plus vector. Where the plus is that one. So what it means is that this vector here, this superposition of 2 4-dimensional vectors represents physically a quantum bit in the 0 state, spin up, and a quantum bit that is in the superposition of 0 and 1. Yeah? Cool? You bored, offended? Excellent. Let's do another example. Let's take a superposition of 0, 1, and 1, 0. So I sum them up, I get 0, 1, 1, 0. So again, I want to reverse engineer this and find the 2 vectors A and B that give me that. So let's start from the first element, which is 0. So those are the ones that are easy to understand. So A1, B1, which is the first element, is equal to 0. Okay? So that means that either A1 or B1, or maybe both, have to be 0. So leave it at that for now. Second element, that's not 0. The second element is A1, B2. So for this to not be 0, it means that A1 cannot be 0. So of the 2 options I had here, A1 equals 0 cannot be the right one. Okay? Now let's look at the third element. That's also not 0. That's this one. And that is A2, B1. But for this to not be 0, it means that B1 cannot be 0. Right? So look at this for a moment. The first condition was that either A1 was 0 or B1 was 0. And then I get that, well, A1 cannot be 0, and B1 cannot be 0. So how do I do this? I can't. That's quantum entanglement. That state is a quantum entangled state. That state is a completely innocuous, simple vector in 4 dimensions. But you cannot obtain it as the tensor product of 2 smaller vectors. You just cannot. That is the meaning of quantum entanglement. Like it's almost offensively simple once you look at it that way. Like it's crystal clear. You cannot find 2 vectors that tensor multiplied by each other to give you that one. That's entanglement. Done. Now, let's go back to plain English. What if I try to explain to you in plain English what that means? Well, what it means is that vector over there, if I try to say, okay, that vector describes 2 quantum bits. What is the state of qubit number 1 and what is the state of qubit number 2? Well, they don't have one. They don't exist anymore as individual, separable objects. They only exist in relation to each other. Together, they are a well-defined quantum state of 2 qubits. But alone, they don't exist. So, you know, you hear it already, right? So I say this thing, your mind kind of goes in a spiral. Oh, they don't have alone. But actually, the mathematics is that simple. So if only I could speak like this to anyone who wants to understand quantum mechanics, it would be so crystal clear, right? The other point I want to make is that this thing is not just a curiosity. These kinds of states are a resource. The existence of these quantum entangled states is the reason why quantum computers can outperform classical computers for certain tasks. Here I only gave you the example of 2 qubits, but as you put more qubits in a quantum computer, the number of states like these proliferates exponentially. And these are code words. They are digital code that you can use on a quantum computer that doesn't exist in a classical computer. This is the additional quantum computing resource that quantum computers can use that does not exist in classical computers. Okay? This is really the accelerating power of quantum computers. So now, to wrap it all up, the big why question. Right? So I really made an effort to make this sound all very simple and obvious and so on, but the inquisitive mind may say, but why is that? Why is it that you started off this whole discussion basically just telling me, as if it's some kind of fact of life, that the state of a quantum bit is described by vectors? Why are you authorized to do that? Well, the why question always hits a wall at some point. You can keep explaining things on the basis of more basic things, but at some point you hit the wall. You need to accept something for true. So this description of quantum mechanics that I gave you is true with the lowercase t, you know, of us secular people, in the sense that everything that has ever been observed in experiments is described by that. There has never, in the history of science, been an experiment that, once done properly, could not be described by the mathematics I just showed you. So that is the only meaningful answer I can give you to the why question. That's why we do it that way, because it works. And once you accept, once you know and you are comfortable with it working, you can derive quantum entanglement as simply as I just did in front of you. So then the real question, if you want to go to the philosophy, is why is mathematics so effective at describing the natural world? This is an old paper by Eugene Wigner. That is really the question. Why can't something so simple that we effectively cooked up in our minds, because mathematics is a human thing, is a human language, describe nature at all levels, including the ones that we don't have natural interface with, so powerfully? So this is what I want to leave you with. So just to wrap it up, what we talked about is that language is rooted in the lived experience of those who use it. So the lost in translation phenomenon is what happens when experiences do not align. Understanding means putting new concept in the context of experiences that are lived. That's something that we have as part of ourselves that we can interface with. And quantum mechanics is not part of our lived experience normally, and that's why it has this aura of being weird and counterintuitive, but actually we are creating new tools and new probes to see quantum mechanics. I just showed you the quantum state of a single nucleus. And yet, we do have a language, we've had it for a long time, to stupendously well describe quantum phenomena. Thank you.